Let's try this cubic calculus question here. They give us ax cubed plus bx squared plus cx minus 5, and they give us a nice picture of it here. And we see, oh, this is important. It's turning on an x-coordinate of -1 and 0. And it has another x-coordinate of 5. Well, that kind of means that you can write out the equation. They've given it to you. And you're supposed to show that a is 1, b is -3, and c is -9. But the big trick is, because it's -1, x plus 1 must be a factor, because that makes it 0. See, you put -1 in there. And the other one is 5. Because it turns right there, you square that. Well, that's it. Your whole thing's going to come. You just multiply that out. X squared plus 2x plus 1 times x minus 5. Multiply this all out, and be careful, and you'll get x cubed minus 2x squared minus 9x minus 5. Now, the next part takes a little bit of thinking here. You've got a -5 on the end here, so you know that a times -5 is equal to -5. Well, that means a must be 1. And if a is 1, then everything else falls out. B must be -3, C must be -9. And that's it. That's all there is to it. Let's look at the next question. Calculate the value of x for which f has a local minimum value. In other words, figure out the x value right there at that turning point. That's the local minimum. And you have to just know that you got to, first we can put 1 and -3 and -9 back into the equation. There's your cubic function. You have to take the derivative and make it equal 0. That's where you'll find turning points. So we do that. 3 times x in front, 2 times -3. There it is, -9. Make it equal 0. Divide everything by 3. And that's a nice little easy question to factor. X minus 3, x plus 1. We know that x minus 1 is one of the turning points. The other x value must be 3. Question 9.3. Now this one's a little trickier. To use the graph to determine the values of x for which f double prime of f times f of x is greater than 0. Now how are we going to do that? Well, here's the deal. F double prime, I got to figure it out. So I take the derivative, I get 6x minus 6, and the point of inflection rate here is 1 and -8. I actually looked at a lady that was doing the national exam, and she thought it'd be easier to actually put the graph of y equals 6x minus 6, right? 6x minus 6 in there. So when x is 1, right above this inflection point, when x is 1, the second derivative is 0. That means it's changing concavity. It's positive here. You see it? It's positive above here. And it's concave down when it drops below the line. Why is this such a good idea to do this? Because you can investigate how the second derivative times the function, whether it's greater than 0. Well, when will it be greater than 0? Well, let's just take a place right here. That's negative. The second derivative negative, concave down. But f of x is negative. Well, that would make it work. In fact, right at 1 it works. It just stops working when it equals 1, because then it'll equal 0, and that won't satisfy this. And if they're on opposite sides, see, it's positive over here. You take a vertical line and just compare. It's positive and negative. It's not working. It's not working. It's not working. Imagine this red line going way on forever. But this will be negative, and the line will be positive. It won't work at 5, but as soon as you go here, then they're both positive. So there's some x's greater than 5. It'll work when x is less than 1. The only place it won't work as it -1, because that'll be 0 there. But here it's working. See, it's negative and negative. Whenever the cubic function and this red line here, which is the graph of the second derivative, whenever they're on the same side of the x-axis, like both are negative, then they'll multiply to equal positive. That's a bit tricky, but that's it done.